We are looking at one-step language modeling via continuous denoising by Chan-Yuk Lee, Jae-Hoon Yu, and the team at Keystone CMU today.
Right. And this paper, it is effectively a massive challenge to the entire field of generative AI right now.
Yeah, it really questions that fundamental assumption we've all had, which is that because text is discrete, made of distinct individual tokens, we somehow absolutely need discrete mathematics to generate it.
Exactly. And they introduced two models here to prove their point. The FLM, which is the flow-based language model, and then its distilled version, the FMLM.
And the headline, Finding the Thing, that really kicks this off is just this massive leap in efficiency. They achieve state-of-the-art generation quality using continuous flow matching on raw one-hot encodings. But the killer stat, the one everyone listening is going to be talking about at work tomorrow, is the speed.
Oh, absolutely. Specifically, that they managed to distill this entire model down to a single step of generation.
One step, just one single jump.
One step. And when they run this on the 1 billion word benchmark, it outperforms other few-step models like MDLM and Duo by a significant margin.
We are looking at an 8.3x speedup compared to standard autoregressive baselines. And crucially, unlike previous attempts at one-step generation, it doesn't just collapse into garbage.
Right. It actually matches the performance of models that usually require 8 or even 16 steps. They essentially solved this thing called the factorization error that has been holding back discrete diffusion for years.
And they did it by moving the entire problem into a continuous Euclidean space. So it's faster, it's arguably smarter, and it hints at this unified architecture for text and images down the line.
It's a big deal.
Welcome to AI Paper Podcasts. Let's break this down.
Let's get into it.
So to understand why a one-step model is such a massive breakthrough, we have to look at the current bottleneck, the reality of what we are dealing with right now. If I'm running Llama 3 or GPT-4, I'm dealing with autoregressive generation. Why is that physically slowing us down so much?
It's the serial nature of the compute. Autoregressive models, they generate tokens one by one serially.
Right.
You predict token A, you append, you run the entire massive model again to get token B, append that, and so on. It's like laying train tracks while the train is moving. You cannot parallelize the generation of a sentence because the computation for the 10th word depends entirely on the existence of the 9th word.
So it doesn't really matter how much compute you have. No matter how many H100s you throw at it, the latency is strictly bound by that sequential chain.
Exactly. You can process the prompt in parallel, sure, but the generation phase is strictly serial. And that is exactly why researchers have been pivoting so hard toward diffusion models lately.
Because the promise of diffusion, and specifically discrete diffusion for text, is that you can theoretically generate the whole sequence at once.
Right. You start with a sequence of pure noise or masking, and you refine all the tokens simultaneously across the whole context window.
That sounds absolutely perfect on paper, right? Parallel decoding. Boom. Done. But the authors of this paper argue that discrete diffusion has a fatal flaw, and they call it the factorization error.
Yes. And this is a subtle but really critical point to grasp. To make the math tractable in discrete diffusion, most models have to assume that at each denoising step, the tokens are completely independent of each other, given the current noisy state.
But language isn't independent. Like if I say San Ying, the next word is almost certainly Francisco or Diego.
Exactly. The paper actually uses a great toy example to illustrate why this discrete math breaks down. Imagine a really simple data set with only two valid cities, New York and San Diego.
So a highly correlated multimodal distribution.
Right. If you have many, many steps, if you take your time, the model can slowly coordinate those tokens and figure out which mode it's falling into.
But if you try to generate this in just one or two steps, which is the entire goal for speed, that independence assumption just kills you.
It absolutely kills you. The model might predict New for the first position and Diego for the second position simultaneously.
Because it isn't checking the correlation between those tokens during that specific update step.
Exactly. It treats them independently. So you get New Diego.
Or San York.
Right. And this is a model misspecification. The authors argue forcefully that this isn't just a training issue. You can't just train longer to fix it. It is a fundamental mathematical limit of the discrete approach. The discrete transitions simply don't allow for enough communication between tokens to resolve those strong correlations in a single jump.
So the authors look at this and they decide to just entirely change the playing field. They say, forget discrete math, let's use continuous diffusion for text.
Hence the title, One-Step Language Modeling via Continuous Denoising.
And I have to admit, this is where I got a bit skeptical when I first read the methodology. Continuous diffusion is standard for images, right? Pixel values are continuous float numbers. It makes sense to slowly shift a pixel from a 0.2 to a 0.3.
Right.
But text is inherently discrete. You can't have 50% of the word apple and 50% of the word banana.
Well, you can't in reality. But you can represent them that way mathematically. And they do this by using one-hot encodings in Euclidean space.
Let's visualize that for the audience because it's wild. A one-hot encoding for a standard vocabulary of, say, 50,000 words is a massive vector with 49,999 zeros and a single one.
That's the representation, yeah.
And normally in NLP, we project that massive, sparse thing down into a dense learned embedding right away, a vector of maybe 1,000 numbers before doing any diffusion or processing. Why on earth would they run diffusion on the raw 50,000 dimensional one-hot vector? That seems incredibly inefficient.
It does seem inefficient on the surface, but the authors argue that learned embeddings introduce their own noise into the process. Embeddings tend to drift during training. They require complex regularization to stay well-behaved.
Oh, I see. So the embedding space itself is a moving target.
Exactly. By using the raw one-hot encoding in Euclidean space, they keep the geometry completely pure. They map the text, let's call it Y, to a continuous point X in this massive space.
So they are learning a flow, a continuous movement from random Gaussian noise directly to that specific solitary one in the 50,000 dimensional space.
Yes, they are using continuous flow matching. You can think of it as learning a velocity field, a wind map, if you will. And this completely solves the new Diego problem because the flow they learn is deterministic and continuous. It captures the joint distribution of the whole sequence.
Meaning the wind, so to speak, blows the noise toward New York as a complete unit or San Diego as a complete unit.
Precisely. The velocity vector at position 1 is mathematically coupled to the velocity vector at position 2 in this continuous space. Even if you take a massive leap, even a one-step jump, the direction of that jump is already coordinated. You don't get stuck in the middle with New Diego.
Okay, so the continuous Euclidean space solves the factorization error. It solves the coordination problem. But engineering this must be an absolute nightmare. You are trying to predict a velocity vector in 50,000 dimensions.
It is a challenge, and they use a few very specific tricks to make this work. So let's look at the base model first, the FLM, the flow-based language model. In standard flow matching, you usually try to predict the velocity field directly right. You predict V sub t.
The speed and direction of the noise particle.
Exactly. But they don't do that here. Predicting the velocity directly in this space is really hard because the noise is super high variance. It fluctuates wildly.
And that creates a rank bottleneck in the neural network, I imagine.
It does. It makes training highly unstable. So instead of predicting the velocity, they train the denoiser to predict the clean data x sub 1.
So at every step of the noise process, the model is just guessing. I think the final destination for this token is the word the.
Yes. Because the clean data, that one hot vector, is extremely structured. It is low entropy. It is just a single clean spike in the data. That is a much easier target for the neural network to map to than some chaotic fluctuating velocity vector.
Now, this choice of predicting the clean data leads to something that looked really odd to me in the loss function. Standard continuous diffusion, like what we see in stable diffusion for images, uses mean squared error, MSE. You measure the literal geometric distance between the prediction and the target. But these guys are using cross-entropy loss.
Which is the standard loss function for classification, not usually for diffusion.
Right, feels like they're mixing metaphors here. Continuous space, but discrete loss.
It is a hybrid approach, and it is brilliant. Even though they are navigating this massive continuous Euclidean space, they know the final destination is a probability distribution on the simplex, meaning the values have to sum to 1.
Right, because it's a one-hot vector, ultimately.
Exactly. If you use mean squared error on a probability vector, the gradients get incredibly flat when you get close to the target. It provides a very weak learning signal.
So the model would learn way too slowly at the end of the trajectory.
Very slowly. Cross-entropy, on the other hand, is much more aggressive. It penalizes wrongness exponentially. It snaps the model into alignment much faster. So they're using continuous geometry to move the data, but discrete classification math to cleanly measure the error.
That makes a lot of sense, actually. But then, reading further, they hit another major wall, which is time. The paper spends a ton of real estate on this concept of time reparameterization.
And this is absolutely critical for making diffusion work on text. Look, in image generation, the denoising process is somewhat uniform. You go from a gray, noisy blob to a blurry shape to the outline of a face and finally fine details. It's a very gradual refinement.
But text isn't gradual at all.
No, it's not. The authors point out that text generation exhibits a severe phase transition. For a large portion of the noise schedule, say from time t equals 0 to tit equals 0.8, nothing really happens. The noise is simply too high.
The model literally can't guess the word yet.
Right, and then suddenly it clicks.
In a very narrow time window, the model suddenly figures it out and decides, oh, this noise blob is the word galaxy.
Exactly. If you train your model with uniform time sampling, which means picking random time steps evenly between 0 and 1, you are wasting 80 or 90% of your training compute on the parts of the schedule where literally nothing is happening.
So they change the clock.
They change the clock. They analyze the decoding error rate, which they call P sub E over time. They plotted exactly when that error actually drops.
The phase transition.
Right. Then they reparameterize time, effectively stretching out that critical narrow window. They force the model to spend most of its training cycles mastering that specific phase transition where the word identity is actually decided.
And they claim this was the difference maker for scaling to larger vocabularies.
It was. They scaled to the open web text vocabulary, which is 50,000 tokens. Without this time stretching, the model simply couldn't converge on such a large vocabulary. There was just too much empty space in the schedule.
Okay, so that brilliant engineering gets us the FLM. It works, it generates text via flow. But flow matching intrinsically still requires integration. You have to take many small steps evaluating the network over and over to follow the curve of the flow. But their ultimate goal here is one step.
Enter the distillation phase. This is where they build the FMLM, the flow map language model.
Now, distillation usually involves teaching a smaller or faster student model to mimic a slower teacher model. How exactly do they condense all those integration steps into one?
They use a two-stage process. First, they learn a correction to the Euler step. Essentially, they ask the model, if I try to jump straight from pure noise to the data in a single straight line, how much does that straight line differ from the true curve flow trajectory?
Okay, so they learn a straight line shortcut.
A straight line shortcut, exactly. But they learn to compensate for the error of that shortcut.
Oh.
However, there is a massive mathematical danger here.
Which is?
If you take a massive, unconstrained leap in continuous space from pure noise to clean data in one shot, you might easily land off the map.
Off the map, meaning outside the probability simplex.
Exactly. You might output a vector that doesn't sum to 1, or a vector that has negative values. It fundamentally stops being a valid probability distribution.
And if it's not a valid probability, you can't use that cross-entropy loss we liked so much earlier?
You absolutely cannot. So to fix this, they introduced a technique they call the two-time denoiser.
Which honestly sounded very sci-fi when I read the heading. What is a two-time denoiser actually doing in the math?
It is a strict mathematical constraint. It is a specific parameterization of the network that guarantees mathematically that no matter what the input is or how ridiculously large the time step is, the output will always reliably lie on the simplex. It will always be a valid probability distribution.
So it forces that massive shortcut jump to always land safely on the runway.
Correct. And because it strictly guarantees a valid probability output, they can continue to use cross-entropy loss even during the distillation phase.
Oh, wow.
Most other distillation methods have to fall back to mean squared error because their outputs get messy, which severely degrades the final quality. This two-time denoiser trick allows them to keep those sharp classification gradients all the way down to the one-step goal.
That is extremely clever. All right, let's talk about the results because the proof is in the pudding here. They tested this on the LM1B dataset and open web text. How does it actually stack up against the discrete guys?
The comparison is honestly pretty stark. They benchmarked against MBL, Duo, and Candier, which are basically the current state-of-the-art for discrete diffusion right now.
Now, in the many-step regime, they match right.
Yes, FLM matches them in perplexity. That validates that the continuous approach is at least as good as the discrete one when given enough compute. But the real game changer, the reason we were talking about this, is the few-step regime.
The one-step test.
Yes. At one step, the discrete models fail catastrophically. We are seeing perplexity scores well over 1,000.
Which essentially means the model is just completely confused. It's outputting gibberish.
It's total nonsense. Or they suffer from what's called collapsed entropy, where the model just repeats the word the 50 times in a row. It is the new Diego factorization problem, amplifying itself to the extreme.
And how does their distilled model, the FMLM, perform at one step?
It gets a perplexity of around 104 on LM1B.
104 versus over 1,000. That is a massive, massive gap.
Incomparable. In fact, FMLM, at one single step, performs as well as the heavily distilled discrete models do when given 8 or 16 steps.
So you're getting the exact same generation quality, but 8 to 16 times faster.
And qualitatively, the text really holds up. It's coherent, it's grammatical, and it's diverse. They specifically checked for mode collapse using self-BLEU scores, and FMLM retains the rich diversity of the training data. It doesn't just memorize and regurgitate generic phrases.
This feels like a huge pivot point for the industry. We've been hearing whispers about diffusion for text for maybe 2 years now, but it's always been treated as this academic curiosity because it was frankly too slow or too unstable compared to just standard GPT architectures.
Well, this paper strongly suggests that the instability wasn't because of diffusion itself. It was because we were stubbornly trying to force discrete math onto a problem that desperately needed global context. By moving to continuous Euclidean space, they completely solved the coordination problem.
But I have to ask about the cost here because nothing in deep learning is free. You mentioned earlier that they backpropagate through the entire 50,000-word vocabulary matrix because it's a one-hot encoding.
Yes, that is the major catch here. In standard autoregressive training, like training a transformer with an embedding layer, you only update the specific vectors for the words that actually appear in your current batch. It's a sparse update. It's mathematically very cheap.
But here they can't do that.
Because they are modeling a continuous flow in the full Euclidean space, they literally have to compute dense gradients for the entire vocabulary size times dimension matrix at every single training step.
That sounds punishingly expensive.
The authors estimate it costs about 30% more memory and time during the training phase compared to standard embedding-based methods.
30% overhead is a lot when you're talking about training huge foundational models. That translates to millions of dollars in extra GPC time.
It absolutely is. But you have to weigh that training cost against the inference savings. Training happens once. Inference happens billions of times a day. An 8.3x speedup in inference. That pays for the 30% training overhead very, very quickly in any real production environment.
That's a really fair point. If I'm serving this model to millions of users, API latency and serving costs matter way more than the one-time upfront training cluster costs.
Plus, the authors suggest in the discussion that future work could leverage sparse gradients or various approximation methods to bring that training cost down significantly. It's primarily an engineering hurdle right now, not a fundamental theoretical one.
So zooming out a bit, looking at the big picture, what does one-step language modeling via continuous denoising mean for the broader field of AI over the next couple of years?
Honestly, I think it signals a very real potential unification of our generative architectures.
Unification how, exactly?
Yeah. Well, right now we have a massive divide in how we build things. We use diffusion UNets and DITs for images, audio, and video. But we use autoregressive transformers strictly for text. They are entirely different software stacks, entirely different math, entirely different optimization tricks.
But if text generation is just continuous flow matching in Euclidean space,
then it's the exact same fundamental math as image generation. We are fast approaching a world where a single universal model backbone, a massive continuous flow matcher, could seamlessly handle everything. You plug in an image adapter and it generates pixels. You plug in a text adapter using these Euclidean one-hot flows and it generates natural language.
So no more tokenizers in the traditional rigid sense, just lightweight data adapters funneling into a universal flow engine.
That's exactly where the physics of this paper points us. It highly suggests that the modality of the data doesn't matter nearly as much as the underlying geometry of the flow.
That is such a wild concept to wrap your head around. It would simplify the global AI software stack immensely.
It would.
Yeah.
And it directly challenges this lingering idea that human language is somehow special and it requires its own isolated, discrete handling.
Incredible. For those of you listening who really want to dig into the heavy math, and I know many of you do, I highly recommend pulling up the paper and reading the section on the two-time denoiser. It's a really elegant mathematical solution to that simplex constraint problem we talked about.
And definitely check out the decoding error rate graphs in the appendix. Seeing the visual plot of exactly when a model learns a word, seeing that phase transition mapped out is just fascinating.
A huge thank you to Chanyakli Jahunyu and the whole team at KAIST and Carnegie Mellon for putting out this research. It is incredibly refreshing to read a paper that doesn't just lazily add more layers to a transformer, but fundamentally rethinks the mathematical representation of the data itself.
Absolutely. It's a massive step forward for the field.
Thanks for listening to AI Paper Podcasts. If you enjoyed this analysis, make sure to check out the paper link in the show notes. Think about what a unified continuous architecture could mean for your own stacks, and we'll catch you in the next one.